Systems which have a very low amount of damping are sometimes difficult to control. Think about systems where fluids have to be controlled or pendulum-like systems like a lifting crane. My name is Stef Windrake and in this video I'm going to present to you a simple controller which could be very helpful in these applications, which is the Posicast controller. First, some background information. Posicast is a feed-forward control method that dampens oscillations in systems which are underdamped, and when properly tuned, the control system yields a transient response that has a deadbeat nature. So let's look to the transfer function of an underdamped system, and in this case this is the general transfer function for a second order system, in which K is a gain, omega 0 is the undamped natural angular frequency, and beta is the relative damping coefficient. As we know, when we have an underdamped system, beta is very small and at least smaller than 1. And that leads to a large overshoot and a large settling time. Now let's look to this example in which we have an underdamped system with omega 0 which is equal to 3.14 radians per second, which is equal to a frequency of 0.5 Hertz, and when we have a beta, a relative damping coefficient of 0.2155. And when we add a step to that system and we look to the output, we see this kind of a response. We have a huge overshoot, which is this overshoot, and that overshoot can be measured by looking to the maximum value, subtracting from that value the end value and dividing it by the end value. We can also calculate that overshoot, because the overshoot is equal to e to the power minus beta over the square root of 1 minus beta squared times p. And in this case, using this value for beta, the overshoot is 0.5, which we can see over there. We also can define the peak time, which is the time the overshoot occurs. That time, the peak time, can be calculated by doing the division of p over omega, which is equal to the period time, capital T, over 2. And remember that omega is equal to omega 0, this omega 0, times the square root of 1 minus beta squared. So now we have this is the overshoot and this is the peak time. And now we are going to design a Posicast controller. And step number 1 is we maximize the output to 1. So in this case, the maximum output is 1 plus D, 1 plus the overshoot. So now we are going to scale the input step by 1 over 1 plus D. And that yields a maximum output of 1. So we see it over here, the step has been scaled by 1 over 1 plus D, in this example 1 over 1.5, which is 2/3. This is my input step, and this is the scaled output. And you can see that the maximum value of that scaled output is 1. That was step number 1. At step number 2, we are going to look to the time Tp where the overshoot takes place, and we add from that point on the remaining step, which is 1 minus 1 over 1 plus D, which is equal to D over 1 plus D. When doing that, we get this as an input, the delayed input, and this as the delayed output. So this was the output of the first step, and this is the output of the delayed step. And when we add that together, we can see that this is the shaped input, so the combination of the blue one and the red one, and this is the output, which is the summation of the blue output plus the red output. And you can see the effect of the Posicast controller. We have no overshoot anymore, and we have kind of a deadbeat response. We call this method also half cycle or half period Posicast, which was invented by Professor Otto Smith from 1957, and you probably know Professor Smith from the Smith predictor. So this is in basic the Posicast controller. So comparing the results, this was the result without a Posicast controller, and the blue one is the result with a Posicast controller. So defining the math, defining the transfer function for a Posicast controller, we can say that the transfer function was equal to the reduced step 1 over 1 plus d plus the remaining step, which was d over 1 plus d times the delay, which is in a transfer function e to the power minus s times tp. So this was my delay time. So when we rearrange that to a more common formula, we get the transfer function for the Posicast controller, which is equal to 1 plus d over 1 plus d times minus 1 plus e to the power minus s times tp. Remember, this is the delay and d was the overshoot as defined over here. Tp, the delay, could be calculated by, as we said, doing the division of p over omega. And when we implement this in Simulink, we get this as an implementation for the Posicast controller. 1, the direct feed through over here, that's the 1, plus d over 1 plus d, which is the gain over here, times minus 1. This is the minus 1, because there's a minus over there, plus e to the power minus stp, which is a delay of tp seconds. So, knowing that, we can easily create a Posicast controller by putting that implementation in front of my process over here and putting the step to the input. So, this is in fact a Posicast controller, but it has some drawbacks, because in a classical Posicast controller, it generally suffers from the sensitivity to modeling errors, because when that beta or that omega 0 is not exactly implemented over here, you don't get, of course, the straight Posicast effect as we saw in the simulation. However, you can also use a Posicast controller within a feedback system. And then the design rules for both the Posicast parameters as defined a minute ago and with respect to the tuning of the feedback controller stay the same. So in that case, the feedback controller compensates for error in the Posicast mismatch. So how do we do that? Here we have a feedback system with just a proportional gain. As an example, this is my input, this is my system, and this is my feedback loop over here. Here we have our Posicast controller, and we put that Posicast controller exactly at this place in my feedback loop, so behind the controller over there. And as I said, the design rules for both the Posicast parameters and with respect to the tuning of the feedback controller stay the same. And then we see this as a response. This is the response without a Posicast controller, and the blue one is the response of a system with the integrated Posicast controller over here. And please note that if the implemented delay in the Posicast controller is not an integer number times the sample times the sample time, this will also cause a mismatch, because then we don't have the exact delay implemented in the Posicast controller. So conclusion, a Posicast controller really helps in getting a much better step response for systems with a low amount of damping, and the implementation of a Posicast controller is quite easy and really straightforward. In the next video, I'm going to present to you a simulation of the impact of a Posicast controller on the lifting crane. Thank you for watching, and I'll see you next time.